Imagine for a moment that you woke up today with a perfectly functioning brain, capable of solving the most complex calculus equations and performing logical deductions with lightning speed. Yet you possessed no memory of the second that just passed. You could calculate the trajectory of a rocket, but by the time you reached the end of the equation, you would have forgotten why you started it. This is the existential crisis of the logic circuits we have built so far. In our previous explorations, we constructed adders and arithmetic logic units, ALUs, miraculous engines of pure thought, made of silicon and copper. But they were stateless. They were calculators with amnesia. Today we are going to fix that. We are going to dive into the architecture of remembrance and discover how we can use the very same transistors that calculate sums to create a permanent record of the past. To understand how a computer remembers, we must bridge the gap between forward-flowing logic and circulating state. Our journey follows this path, the conceptual shift, moving from circuits that calculate to circuits that hold. The power of feedback, using OR and AND gates to lock in a state. The latch, combining behaviors into a stable 1-bit memory element. The gated control, introducing write enable to prevent accidental changes. Scaling to registers, grouping bits into bytes for meaningful data. The matrix revolution, overcoming the wiring nightmare by organizing memory into a grid. Addressing and decoding, learning how to find a single bit among billions. The abstraction of RAM, seeing memory as a simple list of bytes. SRAM versus DRAM, understanding the physical trade-offs of modern hardware. We mastered the art of combinational logic. We took transistors, those tiny electronic faucets, and wired them into gates. We built an ALU that could add, subtract, and perform Boolean operations. It was a masterpiece of now. However, the moment you turned off the input switches, the answer vanished. The fundamental difference between a calculator and a computer is state. A computer needs to know where it is in a program. It needs to store the result of step A to use it in step Z. To do this, we have to change the way electricity flows. In a standard logic gate, the signal moves like a river, from input to output. To create memory, we need to create a whirlpool. We need to feed the output of a circuit back into its own input. This is the feedback loop, the foundational, moment of computer science. Let's start with the simplest version of feedback. Imagine an OR gate. An OR gate outputs a 1, if either of its inputs is 1. Now imagine we take the output wire and loop it back to one of the inputs. If we momentarily tap the other input with a 1, the output becomes 1. But because that output is wired back to the input, the OR gate now sees a 1 on its feedback line. Even if we remove our original finger from the button, the OR gate keeps telling itself to stay on. It has remembered that a 1 once happened. It is now a permanent 1 machine. Conversely, look at an AND gate. If we loop its output back to its input, and the initial state is 0, it will stay 0. Forever, because an AND gate requires both inputs to be 1 to turn on. If one input is the feedback loop, which is 0, it can never become 1. These are the two pillars of stability. One circuit is sticky for high voltage. The other is sticky for low voltage. But a memory that only stays at 1 or only stays at 0 is useless. We need a circuit that can do both. By cleverly combining an inverter, a NOT gate, with our feedback loops, we create the senior latch set-reset latch. Think of this as a physical seesaw. When you hit the set button, the circuit flips into the 1 state and stays there. When you hit the reset button, it flips back to 0 and stays there. This is our first true 1-bit memory. It is a tiny electronic light switch that stays where you put it. However, we hit a snag. In the raw senior latch, if you press set and reset at the exact same time, the circuit enters an invalid state. It's like a person trying to say yes and no simultaneously. The logic breaks down and the output becomes unpredictable. In the world of engineering, unpredictability is the enemy. We need a way to control when the memory is allowed to change. To solve the chaos of the senior latch, we introduce a third input, the write enable or clock signal. We place AND gates in front of our set and reset lines. Now, the memory doesn't care if the data inputs are flipping around like crazy. Unless the write enable wire is turned on logic 1, the inputs are blocked at the gate. This creates the gated D-Latch. It has one data input D and one enable input E. If enable is off, the bit is locked. If enable is on, the latch opens and whatever value is on the data line is stored. When you turn enable back off, the value is frozen in time. This is the fundamental atom of all digital memory. Your phone has billions of these. A single bit is barely enough to remember if a light is on or off. To store a number or a character like the letter A, we need more. By grouping 8 of these latches together and tying all their write enable wires into one single master write line, we create an 8-bit register. Now, when we pulse the write enable, we store 8 bits of data simultaneously. This is a byte. It's a hardware-level variable. But here's where we hit a wall. If we want to build a computer with just 1 megabyte of memory, which is tiny by today's standards, and we use this register method, we would need millions of wires running across the motherboard. The back of the computer would look like a plate of spaghetti gone wrong. We need a more efficient way to organize these bits than just stacking them in a line. Instead of a long line of registers, we organize our latches into a grid matrix. Imagine a giant checkerboard where every square is a 1-bit latch. To find a specific bit, we don't need a wire for every square. We only need wires for the rows and the columns. This is the birth of the memory address. If I want to access the bit at row 3, column 5, I send a signal to a row decoder and a column decoder. The row decoder takes a binary number, like 011 for 3, and activates exactly 1 row wire. The column decoder does the same for the columns. The latch sitting at the intersection of those 2 active wires is the only one that gets to talk or listen. This multiplexing reduces the number of wires from millions to just a handful. Now that we can find a bit, how do we talk to it? We modify our latches so they share a single data line. We use a series of AND gates to ensure that only the selected latch can put its value onto the shared wire, reading, or take a value from the wire, writing. We add a read-write control signal to tell the memory which direction the electricity should flow. At this point, we stop looking at the individual transistors. We abstract. To the outside world, this complex grid of thousands of gates looks like a simple black box. You give it an address, you set it to read or write, and you provide the data. This is exactly how a software programmer interacts with memory. They don't care about the feedback loops. They only care that the value they put in at address 100 is still there when they look for it later. To store full bytes instead of bits, we stack 8 of these matrices on top of each other. When you select address 50, you are actually selecting the 50th bit in 8 different grids simultaneously. These 8 bits come together to form 1 byte. This structure is what we call RAM, random access memory. The memory we just built conceptually is known as SRAM, static RAM. It is called static because as long as the power is on, the feedback loop keeps the data alive forever. It is incredibly fast, which is why it's used for CPU caches. However, it's expensive because each bit requires about 6 transistors. In contrast, most of the sticks of RAM you buy for your PC are DRAM, dynamic RAM. DRAM uses a single transistor and a tiny capacitor to store a bit. It's much cheaper and denser, but it has a flaw. The capacitor leaks electricity. It forgets the data after a few milliseconds. To fix this, the computer has to refresh the memory thousands of times per second, topping off the electrical charge. It's a constant battle against forgetfulness. Building memory from scratch teaches us a profound lesson about life and organization. In the beginning, our logic was fast but fleeting. It had no history. It was only when we allowed the output to influence the input, when we embraced the feedback loop, that we gained the power of persistence. In your daily life, you are much like a CPU. You can spend all day processing, responding to emails, reacting to social media, solving immediate problems. But if you don't have a feedback loop reflection, you aren't building state growth. Create your own feedback loops. Just as the OR gate remembers a 1 by looking at its own output, take time at the end of each day to review what you've done. Reflection is the right enable signal for your personal growth. Organize your matrix. When your life feels like spaghetti wiring, too many tasks, too many wires, stop trying to add more wires. Create a system. Use just as calendars, to-do lists, to categorize your focus so you only have to deal with 1 bit of your life at a time. Static versus dynamic energy. Know when to be static, reliable, fast, but expensive energy, and when to be dynamic, efficient, but needing regular refresh. Don't forget to refresh your own capacitors through rest, or you will lose your data, burn out. We have come a long way from a single transistor. We have taught a machine to remember. Next time, we will take this memory and wire it directly into the ALU to create a machine that can finally follow a set of instructions. A true central processing unit, if you could hardwire one specific memory into your own brain so you never forgot it like in SRAM bit, what would it be? Does the idea of dynamic RAM leaking its memory feel like a good metaphor for how we learn new skills? I wish you all great health, mental clarity, and the right enable to store only the best memories in your life. If you found this deep dive into the architecture of memory fascinating, please consider subscribing to the channel. We have many more layers of the computing onion to peel back, and I'd love to have you on the journey. Click that bell icon so you don't miss our next episode where we finally bring the CPU to life.